Today's next talk is by Pinyan Liu from Shanghai University of Finance and Economics, talking about counting independent sets and colorings on random regular Bipartite.
Thanks. I would like to thank the organizer for inviting me here and for bringing together this very wonderful workshop. I'm Pinyan Liu from Shanghai University of Finance and Economics, and today I will talk about counting independent sets and counting colorings on random regular Bipartite graph. This joint work with Liao Cao, Lin Jiabao, and Mao Zhenyu. They are my students and postdocs. And first, I would like to point out that actually, similar result was independently obtained by whereas co-author for speaker, and actually I will also borrow everything from Weir's talk and start from there. So basically, my work is a kind of application of this general approach using this polymer model. And one thing differential our work from the previous computed partition function for this post model is that we actually not only using this ground state, but we're using something called ground cluster. It's a family of configurations rather than a single one. In the previous talks, we said that it's like red, or all blue, all white is a kind of ground state and some deviation from that. Here, it's not single state. We talk about a ground state, a ground cluster. So here, it's actually a common recipe how to design algorithm using this approach. First of all, we identify ground states for the problem. Then we define the neighborhoods of these ground states and prove that their summation is actually a good approximation of the original counting problem. Then we define a polymer model for each ground state to represent the deviation from these ground states. And then we prove that actually this polymer model is a good approximation. Then we verify this KP condition for the polymer model, which we are given as a FP task for the problem. Okay, that's actually a common recipe for both of the two problems I'm going to present in this talk.
KP is Katetsky price?
Yeah. This is a more picture view. So this is a space we want to count, or a kind of partition function we want to compute. Then we want to identify some ground states. So it's a family of states, kind of it's large, and they may overlap with each other. And then we define a neighborhood of these ground states. And we want to prove that actually we summing over all these neighborhoods or ground states, they will give a good approximation of the total set, which means that the configurations outside all the neighborhoods are very small, and also the intersection of these ground clusters are small, so we don't really double count too much. Okay, that's the thing we want to prove. And then once we get that, for each ground state, a ground cluster and its neighborhood, we define a polymer model and to show that this polymer model actually satisfies this KP condition. Okay, let's start with, one thing, as my title suggests, we are counting the independent sets and coloring for random regular Bipartite graph. Actually, we don't really use too much property about this random regular Bipartite graph. We only use the kind of expansion property of this family of graph. So one expansion property is that when a set choosing from left side or right side is small enough, then the expansion is large. So this expansion property is indicated by two parameter alpha and beta. Usually beta is very large, alpha small. And this another property we call covering property. It's kind of an extreme of the expansion property, which says that as long as the set is large enough, its neighbor almost covers the other side, except a small fractional. Okay, it's easy to prove that when the degree delta is large enough, a random delta regular graph almost surely has this kind of good property. I'm not specify the parameter, alpha, beta, S, and delta, how they relate to the degree delta, because we will choose different parameters for different problem. But the roughly idea is that this alpha is very small, and alpha, S, and delta small. When delta is approach infinity, they approach 0. And beta is close with delta, could be linear, or as a linear in delta, or as like a square root of delta, things like that. Okay, that's the only thing we use for random graph. Okay, we start with counting independent sets. So counting independent sets for Bipartite graph is actually a very important problem in the field of approximate counting. It is conjectured to have intermediate complexities, may not have FP task or PRAS may not as hard as NP hardness. Okay, so it also plays an important role in the classification because many other problems prove to be BIS hard or BIS equivalent. So this is a very important problem. From the algorithm side, with Jingchen Liu, who is also here, we prove that we obtain an FP task for the BIS problem when actually one side degree is bounded by 5. We don't have any requirement for the other side. For this particular problem for BIS on random regular Bipartite graph, it's also important. There are at least two reasons. One is that it's easy to show that the MCMC is also slow mixing when delta is sufficiently large. Actually, if delta is larger or equal to 6, it's already slow mixing. The other thing is that in the hardness proof for the independent set, actually this random regular Bipartite graph is an important gadget which plays an important role here. So these are some backgrounds. Okay, now let's follow the recipe to give an algorithm for that. Okay, for this independent set problem, we actually identify two ground clusters. First class is that this is independent set which is entirely choosing from the left side. If the set is entirely choosing from the left side, they are always independent. Okay, because it's a Bipartite graph. Or the independent set which are entirely choosing from the right side. They are all. So each cluster contains 2 to the n many different independent sets. They are not single independent sets, but they are a family of independent sets. And now we define a neighborhood of these two clusters. We think that if an independent set is almost choosing from one side, say, if it is really in intersection with the left side with a very small fraction of nodes, we call it the neighborhood for this IL, and similarly we can define IR. Okay. Now the idea is that we want to show that summing over the independent sets in IL and RR is a very good approximation of all the independent sets. That's actually quite easy to prove. First thing is that I want to show that the intersection of these two sets is very small, so we don't really double count too much. And this is because for independent set choosing from the intersection, it actually takes at most alpha n nodes from each side. Then we can count the number of all possible such independent sets is n choose alpha n square. And if this alpha is small enough, this number is very small comparing to 2 to the n, because 2 to the n is the size of the cluster.
So can we go back to the definition of IL?
Sure. Sorry. So this is saying that their intersection is very small. And we also show that the independent set which is outside both set is also very small. That's also quite easy to show. We're using this covering property. So if the independent set takes Sn nodes from one side, it will cover almost all the other sides. So from the other side, it only can take alpha n nodes, so it belongs to this family. So if it's not belong to this family, it means that it can take at most Sn nodes from both sides. Okay. Given that, we can also count the number of all possible such independent sets, and with S small enough, this number is exponentially small compared to the. Okay. So now we can compute the size of IL and compute the size of IR and sum them up, which is a good approximation. Now, we define a polymer model for one of them, and actually they are symmetric. So let's recall that this is the definition for IL. So it's a deviation. So this IL is not a single configuration. So a deviation from that means that because in this cluster we want to choose the entire subset from the left side, say. All the nodes choosing from the left side is kind of a deviation from the ground cluster, right? So for each independent set in this set, the connected components of the deviated nodes, which is the intersection of the independent set with the left side, and is kind of the points for the polymer. And but we define, as in the previous talk, this polymer is a family of connected component. But here we have to define this connection with respect to G sub 2 rather than G rather than in the already graph. If the two vertices are actually within distance 2 in the already graph, then we say that they are connected. We define the connected components in that sense. Otherwise, we cannot really cover the original problem from this polymer. So I will give a picture. Then we can define this gamma star to denote all the possible polymer, and this compatibility of polymer defined similarly, but also with respect to G2. And this definition actually have the property that two comparable polymers don't share any neighbors. That's actually equivalent definition of within distance larger than 1 in this graph. And we using this S gamma star to denote all sets of compatible polymers. So let's give a picture. So here, this is the left side, this is the right side, and most of the nodes choosing is from the right-hand side, but it's omitted here. And some nodes are choosing from the left-hand side. So these are the nodes choosing from the left. And then these are the deviations from the ground states. Then we actually group them using the connect components. These three nodes are connected in the G2 because they share some neighbor together. And this is a singleton, and this is a singleton. So for this, we have three polymers. Okay, now we want to define the weights of the polymer, like in the previous paper. So what is the meaning of the weights of the polymer? Basically, this means that once you're choosing some vertex from the left side, this will have the consequence that we cannot no longer choose any of his neighbors, right? So basically, for each neighbor, previously it has two options, occupied or not occupied. Now you only have one option which is not occupied. So this is 1/2. Basically, is a ratio affected by the fact that you are some vertex in the left hand side choosing. So this is a weight function. This is just a formal variable. I think with the new algorithm as present in the previous talk, we actually can ignore that part, just choosing z as 1. But previously we are using this zero freeness, and this z is the formal variable. We want to show that the partition function is zero free with respect to z up to some point slightly above 1. Then we can compute the partition function at the point z equal to 1. Okay. So now with this nodes, with these weights, we can define the partition function for the polymer, which is exactly the same with in the previous talk. This is summing over all the collection of compatible polymers, and for each collection, we take the product of all the polymer in the set and of their weights. Okay, and the relation here is that by choosing these weights in this way, the size of this IL is exactly equal to 2 to the n times this partition function of the polymer, but with a global constraint that the total size of the polymer is not larger than alpha n, because this is a constraint for the IL. Given that, everything else is just a 1-to-1 correspondence. So this size is exact to this partition function, but with a global constraint. Okay. So, but we don't really like this global constraint because the theory of polymer partition function without a global constraint. So one thing we want to show is that we can actually safely just just slow away this constraint, and this is still a good approximation. Because the reason is that this weight function is of kind of exponentially decay because this beta is expansion with line. That's the main idea. So we can discard this global constraint just to compute the partition function for the polymer model. It's also a good approximation for the size we want to compute. Okay. Now the only thing we are left to verify is the KP condition, and let's recall this is the inequality for the KP condition. So we are for a particular given polymer gamma star, we sum over all the incompatible polymer gamma with this quantity, and we want to bound that by the size of this gamma star. So in this summation, we want to enumerate all possible polymers which is incompatible with gamma star. So we basically this gamma must be either intersect with this gamma star or share some neighbor with him. So basically we will enumerate a vertex which is in this polymer or its neighbor. So the polymer gamma must contain at least one vertex from this set. Okay, this is not too large. Then we enumerate the integer k, which represents the size of the polymer gamma. Then we finally enumerate all the possible polymer gamma containing this vertex v and with size k. And this is a kind of a way to bound this summation. So here is the possible number of v's. So it's because the degree is bounded by delta, so it's the 2 times delta square. And this is summing over this part is all possible connect components of the graph containing v. And this ek is just this ek because we are just summing over the polymer with size k. And this 2 to the minus beta k is a weight function, up bound of the weight function. This is z, is just a z something. So we have some this kind of expression. Now by choosing this, since this beta is a growing function with delta, something like linear or square root of delta. So this is exponentially small term. So by choosing delta large enough, we can make this one small enough, even kill this delta square in the front. And so everything is less or equal to the size of the gamma star, which is the requirement for this KP condition. Okay, I will omit detail here, but everything is quite clear. Okay. Now, with that, we can actually set the parameter ret and prove that if this delta is larger or equal to 53, there's a FP task for this bipart independent set for almost every delta regular bipart graph. And we can also extend this result for the Haddock model with parameter lambda. Then as long as this delta is larger enough, I mean, it's sufficient large, then a constant, and also this parameter lambda is larger or equal to this value. Basically, if we are fixed lambda, we can choose delta large enough to satisfy this inequality. There is a FP task to compute the partition function with Haddock model. Let me recall that if in the original BIS problem, if delta is less or equal to 5, we actually have an FP task backward decay. Also, for the weighted case, if lambda is less or equal to this quantity, this is almost like in the order of 1 over delta. We have a FP task backward decay. Then our new theorem says that if lambda is large enough or if delta is large enough, actually we also have a FP task. But something in the middle is missing. Like, how about from delta from 6 to 52 will happen? I mean, we can for sure to optimize this, but it's not likely we can optimize all the way to 6. I think there's something in the middle they are missing.
Almost every in the sense of this random regular?
Yeah, in the sense of this, if you are choosing a uniform.
Can you say anything about random graphs with average degree delta?
Sorry, average degree, that's unclear. Yeah, we have to talk about this GNP model. We don't know yet. Okay, this finishes the independent set part. Now let's count coloring. Okay, count coloring is also another kind of extensively studied problem in the area of approximate counting. Of course, mainly for general graph, not necessarily bipart. But for general graph, we have to make this Q is larger, at least larger than the maximum degree to make sure that there exists a Q coloring. And so all the studies from there. But for bipart graph, it's very different because for any bipart graph and for any Q is larger or equal to 2, there exists a Q coloring for the bipart graph. And it was also known that counting Q coloring on bipart graph is actually BIS hard. But I think it's not known to be BIS equivalent. That's the situation. Okay, but now we are sure that when this degree is large enough, we can actually count the Q coloring on a random bipart graph. Okay, now we follow actually exactly the same recipe, but it's more involved way because coloring is more complicated than independent set. Okay, so here now first step is identify some ground clusters for this coloring problem. So here it's actually the ground clusters are indexed by a subset of the coloring. So the ground state is that by a fixed x, which is a subset of all possible colors. We actually color everything from the left side by a color choosing from x, or all the right-hand side was choosing color from x, the complement of x. So for every choice of from these families, they are proper coloring because we are choosing different colors from different set for different side. And for bipart graph, this is also always a proper coloring. So we also define the kind of the neighbors of this of this ground cluster, which means that the coloring is very close to that, meaning that deviation from this ground cluster is bounded by alpha n, which means that the nodes in the left side, which is not colored by colors from x, is plus the number of nodes in the right hand side, which is colored by the colors from x, are small. Okay, similarly. And in particular, it's easy to see that if this x is close to the size of x is close to half of q, it actually gives the largest cluster, and their size is computed by this 2 over 2 by the 4 or the ceiling. Okay, some facts, some simple facts. Specific facts is that if two integer a and b, the summation is less or equal to q minus 1, then any possible a to the n times b to the n is exponentially small compared to this quantity. And also, if they are summing up to q, but they are not close enough, they are not half-half, if their difference is larger than 1, this quantity is also kind of exponentially small comparing to the cluster we are considered. Okay, so now we want to prove that summing over all these possible neighborhoods of the clusters gives a good approximation of the possible coloring. The first thing we want to show is that the intersection of these clusters are very, very exponentially small. This is easy to see because for Cx and Cy, then most of the left-hand nodes are colored by color from the intersection of x and y, and for the right side is from the intersection of x bar and y bar. Then if x is not equal to y, there are something in the symmetric difference, and so these two numbers, the summation of these two numbers is at most q minus 1. And given the mathematical fact we showed, the number of such coloring is exponentially small compared to the size. Okay, and we also want to show that the coloring outside all the neighborhoods of this cluster is exponentially small. Then we're using the covering property, and we can show that there kind of at most Q-1 colors are used by at least Sn nodes, and then we choosing this S small enough. You can show that the number of colors in this set is exponentially small. We can further show, as I already mentioned, that we only need to sum over all the ground cluster with the size x is approximately half of Q, and because anything else is exponentially small. And also by the symmetry of this coloring, Cx and Cy are all same size as long as the size of x and y are same, because there's symmetry of coloring. So basically, it's end up with a very good, very simple algorithm for even Q. You only need to compute the size for this particular cluster, which is choosing colors from 1 to half Q from left side, and half Q plus 1 to Q for the right hand side, which then times this other possibility Q choose half Q is a good approximation. And for odd Q, it's slightly different but similar. Okay. Now, we already show that this ground clusters and their neighbors is a good approximation for the set of all proper coloring, and now we define the polymer model, which is represents the deviation from this ground clusters. So that deviation is also easy to define. Basically, all the nodes which is not colored as what you expected. Okay, so basically the nodes from the left side which not colored by the color from X, and also the nodes from the right hand side which not colored by colors from X bar. Similarly, we also define the polymer model as a connected components for these deviated nodes, but also with respect to this G2, not the original graph G. And everything else is similar. Now, here is an example. This is like a 3 coloring, and we are looking at the clustering where all the left-hand side is colored green, colored red, and all the right-hand side nodes are colored by blue and yellow. So, these are deviated nodes because they should be colored red, but they colored by yellow and green here, and they should not be colored by red, but they colored red. Okay, then we also, for these deviated nodes, choose the connected components with respect to G2. These 4 nodes are actually connected by G2 because these are share some neighbors, even although the neighbor is outside this polymer. And also this here is another polymer with another connected component. Similarly, we define the weight of a polymer, which represents the kind of the effect this polymer have to his neighbor. Basically, like we can actually take product over all the neighbors of this polymer, and because for this nodes, since it connects to a vertex in the polymer, which is colored yellow. Previously, these nodes have 2 choices, which one is yellow, one is green, but now it only has 1 choice, which is blue. So it will contribute a effect of like 1/2 and something. And this polymer partition function and this relation is the same, also with this global constraint. And we can also safely discard this global constraint due to the fact that this weight of polymer is kind of exponential decay. This is the decay rate. And since it's exponential decay, or if the total size is large, this number is small enough. Okay, and basically due to the same reason, we can verify this KP condition almost identical. Except we are with a different decay rate. One thing is different here. For the independent set, once you have the support for polymer, everything is fixed. But here, except the support of the polymer, you also need to enumerate all possible coloring on this vertex, and so I have an additional factor q to the k here, which is the upper bound of that. But anyway, since this beta grows as a function of delta, we can always choose delta good large enough to make this small enough to even kill this delta square. Very, very similar philosophy, but if you want to set all the parameter correctly, there's some mess to do, but that's not essential. Okay, by this we can prove that for any q which is larger or equal to 3, actually for 2 there exists exactly counting algorithm. So if delta is larger enough as a function of q, here this should be some polynomial of q. There's an FG task for counting the q coloring of almost every delta regular Bipartite graph. Some open questions. One is try to close the gap. As I said, I think the up bound can be further optimized by some more careful analysis, but it's unlikely that it can be bring all the way down to the uniqueness, or to the opposite of this FG task for collision decay. So,
do you think there is an FP task for these class of graphs for all delta?
Sorry?
Do you think there is an FP task for this?
I don't know. Oh, this should be a question mark. That's an open question. I don't know. Yeah. I don't know. I would guess yes, but but it certainly requires some new technique, and another open direction is that try to apply this new approach to other counting problem. In particular, you can try this base hard problems or the problem with slow mixing MCMC. Basically, it's really have a kind of opposite effect. It's sometimes slow mixing, we actually can help us to decompose that into different ground clusters and using this polymer. Okay, that's all. Thank you.
What is the function, the q of delta?
Q. I think in our paper we get like q to the 10th, but in various papers we actually have that like q to the q square or q square, yeah.
It should be q.
Should be q.
Q log q.
Right.
Okay, yeah.
Any other questions?
Does the method work at all if there are a tiny number of edges inside the what should be, if you just make a graph slightly non-bipartite, put a tiny number of edges inside each part? Can you say anything at all?
It really depends on the model, right? So it's how tiny, and if it's really tiny, I think so, but yeah, I don't know.
So, let's say we have this even set and random regular Bipartite graph. When you choose the ground state, you are sort of parameterized by, let's say, the fraction versus chosen, right? Now what you are choosing is 1, 0, and 0, 1. But these are not the sort of the maximum energy states, right? If you parameterize by the fraction versus chosen on left and on right, the maximum energy is something close to 1, something close to 0.
Yeah.
Would that help somehow?
Yeah, that's actually something in my mind. I think it's towards trying to attack the middle. Yeah, but it's complicated because once you're choosing a ground cluster which is not entirely 0 and 1, then it's not uniform. The weight function is hard to define. It's like yeah, I agree with you. Yeah.
Can you speed up the computation by using that most of the polymers are 3-like? I mean, practically they should be the same for every graph, so a large chunk of the sum should be the same, I guess.
Well, what do you say?
I mean, certainly with the expansion, it speeds up a lot. I mean, it's not like but you try and use some symmetry. This is probably true.
No, practically, I believe that the first, if we don't consider any cycle, then I guess it will simply give the better approximation. And then I guess if we know the number of 4 cycles, 6 cycles, 8 cycles, and so on, then it gives a lot of improvement. I guess even a finite number of cycles will tell you, say, within factor 3 or factor 10, the number of independence, let's say. And then if you want really good approximation, I guess you really have to go up till log n. Polymer.
I mean, there's results using the second moment method by Sly and Sun that actually show exactly what you're saying. And small subgraph conditioning would say you just want a 1 plus epsilon for constant epsilon. And it's concentrates.
In terms of one of the open problems, the one I think Bruce was asking about, yeah, that one. Are there results known on the girth condition for sharp bits?
I don't know.
So maybe, so you said that the random regular graphs were an important gadget in hardness or bis hardness for many problems. So
No, it's actually NP hardness for, I mean, also, maybe also bis hard. I mean, for the yeah. Sorry.
Suppose that the answer is yes to the question, so that for every delta you can do it. What kind of consequences would that give? Maybe is that easy to see, or is that?
There's no consequences. Yeah, basically in the gadget size, they're also showing that the behavior of this is quite regular and using the fact to prove the hardness. So even if this is easy, it's not have a consequence for that.
We take Sly's hardness thing.
Yeah.
You just don't have that expansion, right? Like you have expansion within the gadget, but then you connect the terminals in a really non-expanding way.
Yeah. This is just a gadget, not entirely graph, and the hardness from the other part. Yeah.
So for, say, to count the number of stable matches or something.
Oh yeah, that's a question we I don't know. Yeah, that's interesting. I mean, because this stable match really have a quite different structure, and it's not even clear how to define expansion or random in stable matching. Yeah, I think that's certainly one very interesting problem because it's have really different flavor and yeah.
Any more questions? Okay, I think we have a longer break till 11:45. Thanks again, Pinyan.